Well, one of the major topics that we work on in calculus is this notion of maximizing and minimizing functions. In a business environment, if you have a profit function, you want to maximize the profit, minimize the cost. So finding maximums and minimums is one of the major components of what you will use calculus for in a real-world environment. So in a graph that looks something like this, there are kind of key, obvious maximum and minimum places. These 3 points are what's called local maximums and minimums. Well, some of them are. And by that, what I mean is this. That's what's called a local maximum. Now, and when I say the word local, what that means is just kind of near that point. So as long as I'm near this particular x value, that blue dot is at the local maximum. And it's local because there's higher answers somewhere else. So it's not the what's called global or absolute maximum. Global or absolute. This one would be the absolute or extreme value. Absolute, global, extreme, maximum value. Nowhere on this graph is there a point that's higher than that point up there at this particular x value. Now let me emphasize something with you. There's a difference between where the maximum occurs and what the maximum is. If I had another graph that went like this, these two graphs have the same x value, but they have different y values. And so make sure you're reading the question when you answer a question as to what is the maximum. If I'm saying where does the maximum occur, that's the x value. What the maximum is the y value. So a real life scenario would be a company, your profit is going to be maximized when you make 1,000 items. But what the profit is depends upon the y value. So one company maybe makes 1,000 items and their profit is $5,000. But a different company makes 1,000 and their profit is $10,000. I'm just making up some numbers. So the idea being the difference between the x and the y values there. So where it occurs is an x value, and what the actual value is, the value of the maximum is a y value. This point, of course, as you can see, is a minimum. But this would be a local minimum because there are other points that are smaller answers. So local maximums, local minimums. This particular graph, notice the arrows on the end, has no absolute minimum value. So look at this equation. Graph this on your calculator. Pause the video here for a moment. Get that into your calculator and graph it. The question will be to find the local maximum and minimum values. So let's take a look at the picture and see what it comes out to be. Something more or less sort of like that. I forget what the scale is, but we can see that there looks to be a minimum value out here at 2, and it looks to be a maximum value at -1. Well, again, those are local maxes and local mins because the graph keeps on going down, the graph keeps on going up. But notice what's going on at those points. The key thing, the key element to that is at those maximum and minimum values, you've got a horizontal tangent. And if you've got a horizontal tangent, the way to go about finding the maximum and minimum values is to take and set the derivative equal to 0. So this French mathematician, I believe his name is pronounced Fermat. Yeah, Fermat is how a French person told me they would pronounce it. So look what this says. If f has a local max or min at c, then f prime and f prime of c exists. There has to be an answer there. Then the derivative at that point, must be equal to 0. So we're not going to use that much, but we're going to talk about that and get into that idea. Now, let me talk about a little bit. We're not going to use this theorem a lot. We'll use this notion, but not necessarily cite this theorem. But here's a key part of this thing. F prime of c has to exist. Now, at this point, the derivative doesn't exist. Because if you remember what the derivative is, here's the long version of it. It's that limit of the difference quotient I'm going to use the right letters. So f of x plus h minus f of x all over h. Remember, this is just the slope. And so what has to happen for the derivative to exist is the slope needs to be approaching the same value from the left and from the right. So from this side, this looks like it's -1. From this side, it's +1 slope. And it doesn't approach the same value at that point. So at this particular case, even though I have a minimum value, the derivative doesn't exist. We'll talk more about that as we go along. So how do I find the maximum and minimum points? Well, you take the derivative. There it is. And you set it equal to 0. That's how you maximize or minimize a function. So solve, and I find out where the maximum and minimum occurs. Now, we spent a ton of time last year talking about the shapes of graphs. You're supposed to be able to look at this graph and know that the basic shape looks like this. So even though -1 is a smaller number, the maximum, the local maximum, is going to occur at that -1 point. It occurs to the left because I know what the shape of x cubed is. And the minimum point is going to occur to the right at the 2. Those aren't what the values are, that's just where they occur. So if I wanted to find what the values were, I need to now take those x coordinates and plug them into the equation and find out what the maximum and minimum values are. Now you get a little nasty decimal-y thing here. And you can find that, of course, on the calculator if you use the maximize-minimize function. So here's a little fun fact, some vocabulary. A critical number of a function f is a number c in the domain of f such that either f prime of c is equal to 0 or f prime of c does not exist. This is going to be the part that most people are going to forget. Emphasize that, underline it, make a special note of that. We'll spend a lot of time doing that, but there's an occasion where the derivative simply doesn't exist. And we looked at a picture of that a minute ago. If I have some kind of sharp corner there, I can have a critical point where this derivative doesn't exist. And the derivative doesn't exist at that point because the slope is not approaching the same value from the left and the right. So emphasize that some more. So another little piece of vocabulary that we talk about. I think we've used this phrase before, but let me restate it for you. There's a difference between what's called open versus closed. An open interval simply means you're not including the endpoints. So on this one, I'm not including the x value at 2 or the x value at 5. These are not points. This is an interval. In this case, we are including over here the endpoints at 2 and 5. So a graph might look something like this. Where I don't include the endpoints might look something like that, where I do include the endpoints. So here's what this is about. In a graph that goes like this, there is no absolute maximum value. It just increases forever, right? No absolute max. There is an absolute min right there. In this particular case, this graph never gets higher than 3. But yet, there is no absolute max. Now, when I'm at 5, the answer would be 3, but I'm not allowed to actually get to 5. So when I'm at 4.9, I'm making up some numbers. When I'm at 4.9, maybe the answer is 2.99, right? Not quite 3. So let's get a little closer to 5. Let's go 4.99. Now the answer might be 2.999. And every time I get a little closer to 5, this is going to get a little closer to 3. But I'm never going to get to 3. And I can keep getting closer and closer and closer, higher and higher and higher. There is no absolute maximum value to this. On the other hand, over here, there is a maximum value to this one. The maximum value is 3. When I'm at 5, I get the answer of 3. 3 is the biggest answer. So on a closed interval, you always need to check out the endpoints. See what's going on at the endpoints to see if one of those might give you a maximum. Because if I did the derivative, I would have a horizontal tangent there and a horizontal tangent there. But, and so the derivative would equal to 0, but the absolute maximum doesn't occur at one of those 2 points. It occurs at the end point. So you have to check those values of the endpoints when you have a closed interval versus the open one. Open one, I don't need to check the endpoints because those points aren't included in the problem anyway. So look what this question says. Find the absolute minimum on this interval. Well, I've got to have an equation. There it is. So on this interval, -3 to 5, find the absolute minimum. Well, if you graph that equation, that's the one we had a little bit ago, and I set up my x values to go from -3 to 5, you'll get something that looks like this. The horizontal tangents occur at those same 2 spots, but when I find the values at the endpoints, -3 and at 5, now remember I already found the local maxes and mins at those points in the middle, but when I check -3 and 5, I end up with very different answers. Now, this question is about what's the absolute min, so the lowest answer I get isn't at one of these places where the derivative is equal to 0. It's at this spot at one of the endpoints. So that's the absolute min. So this is a key thing, and I've seen this on the AP test a lot, where all on your own you have to remember to check endpoints when you're trying to maximize or minimize a function. You're going to take a derivative, you're going to set it equal to 0, that'll get you these answers, but all on your own you got to remember if they give you a closed interval, check the endpoints. And one other kind of final little twist of things. If I said find the max or min, all right, of this equation, I'm going to take a derivative, got it, set it equal to 0, got it, solve for x, great. X equals 0. Now let me back up. What I have found is a critical point, not necessarily a max and min. A critical point is just simply one of the values that could be a max or min. So maximum or minimum, well, think about what the graph looks like. The graph has to actually have a peak at that point, and it doesn't in this case. Now, the derivative is equal to 0 there, but it's not a max or a min. So here's the thing that you should notice. If I check a number slightly to the left of 0, like -1, if I put -1 into that, -1 squared is 1 times 3, I get 3. And if I check a number slightly to the right of 0, like 1, I also get 3. That's the slope. Remember, I'm checking it into the derivative, so I found the slope over here is 3, and the slope over there is 3. But what tells me that this is not that 0 is not a maximum or a minimum is that there was no change in sign on the derivative. At a maximum point, notice that the slope is positive over here, but on the other side, it's negative. So you got to look for that change in sign. That was it, kind of fast and furious. If you have questions, by all means, check with me in class.